Okay, today we're going to look at a weak acid equilibrium problem where the concentration of my acid is close enough to the Ka value that we're not going to be able to disregard the x that's in our denominator, which functionally means that we're going to be using the quadratic equation. So if we have our problem here, we are given a concentration of nitrous acid, so that's my HNO2 coming from the nitrite ion, recall. And if we're given a concentration and we're given information about it reaching equilibrium and we have an equilibrium constant, then that should trigger icebox or ice table. So if we think about our icebox here, then our initial concentration is given in the problem. We're going to ignore our water here, and we don't start off with anything in terms of our products. In terms of the change, it's a molar quantity, a molar ratio of 1 to 1 to 1 to 1. So we're going to get rid of a molar quantity x here, gain molar quantities of x here. And so at equilibrium, these are my equilibrium concentrations in terms of variables. So now, if we set up our expression for Ka, remember that's the concentration of my products over the concentration of my reactants, then my Ka value is 4.5 times 10 to the negative fourth. So if we think about this value, 4.5 times 10 to the negative fourth, what does that tell us about this equilibrium? Well, it's smaller than 1, so that means that my denominator is larger than my numerator, which means my concentration of my acid is greater. So again, that means that I have a weaker acid because it's not completely dissociating. That's going to be equal to my concentration of my products divided by my concentration of my reactants. And again, we're disregarding our water. So we have x squared on the top here. We can't disregard our x here because if we look at the magnitude of my Ka value compared to the magnitude of my concentration, so these guys are pretty close together, so I can't disregard x, which means that I'm going to have to use the quadratic equation. So when I do some algebraic rearrangement here, then I end up with 0 is equal to x squared. And I'm skipping some steps in my algebra. So as always, if you have questions about those specific steps along the way, then don't hesitate to ask. So if I rearrange and solve and combine like terms, then I end up with this, which means in my quadratic equation, my a is going to be equal to 1. My b is going to be the value that precedes my x. My c is going to be the one that doesn't have a variable associated with it. And recall that the quadratic equation is minus b plus or minus the square root of b squared minus 4ac all over 2a. So there's computer software that you can plug this into. I know that some of you have this programmed into your phones. So however you go about solving this, you end up with two answers. You end up with two values, and this is true with any of these types of problems. So we need to evaluate those answers. So when I plug those in, then I get an x that's equal to 1.29 times 10 to the negative third and negative 1.74 times 10 to the negative third. So these are my two values. So I need to think about them. That's a 7 there. So I need to think about them in terms of physical quantities, right? Because our numbers represent physical things. And we know that this represents a concentration at equilibrium, so it can't be a negative value. So we're going to disregard our second answer here because it's negative. So that means that my x is equal to this. And now that gives me my equilibrium concentration of hydronium. So my H3O plus at equilibrium is equal to 1.2 times 10 to the negative third. And again, I've been growing sig figs along the way. We know that we're going to be limited to 2 at the end. So I'm just kind of keeping significant figures as I go, and then we'll round at the end per usual. Now the original question asks for the pH of the solution at equilibrium. So the pH, recall, is the negative log of this value, 1.29 times 10 to the negative third. And when I plug that into my handy dandy calculator, I end up with 2.89 as a pH. So again, we want to say, well, does this make sense? Right? Does my answer make sense in a physical way? Well, it's on the acidic side of the pH scale, so that makes sense. It's on a lower number. This is an acid, so that fits, that jives. The number of significant figures I have here is 2. Remember that for logarithms, the number of significant figures past the decimal place is the number of significant figures in the number, because that first digit is really a placeholder on the scale, and then you have your significant figures after that. So this would have 2 significant figures, so 2.89. And yeah, and so that number makes sense. It fits with what we're thinking, and it gives you an example of our Ka values and using those to find pH at equilibrium. So as always, if you have any questions, don't hesitate to reach out. Otherwise, I'll talk to you again soon.